Standard time. Awesome. Well, good evening, everyone, and welcome to the November meeting of the RASC Ottawa Centre. I'm your host, Paul Klauninger, and extend greetings to all of our club members and visitors alike, with a special welcome to RASC members watching us from other centres across Canada. Next slide, please, Chris. Welcome to our meeting. I'm just going to race through this because we have a very packed program tonight, and we are only on Zoom. It's not hybrid tonight. So for those of you that wish to ask a question of the speaker, you can use the Q&A, and a reminder that chat box comments can be seen by everyone. Also, the raise your hand functionality in Zoom is disabled. Next, please. Tonight's program, as I mentioned, is very packed. We have our usual Ottawa skies from Dave Chisholm. Then Jim Thompson is going to talk to us about telescope mounts. We're going to have a very short break, and then Simon Hanmer is going to talk to us about the Earth-Moon distance and some fascinating calculations that go into that. We have an enormous number of observation reports this month. A lot of them came in pretty late in the month, and that's understandable because of the weather conditions that we've had and the opportunities to photograph some of the cool stuff that's in the sky currently. So just a heads up, for those of you that are presenting observation images, please keep your descriptions very brief and moving along, because it's a long list, and as we get closer to the end of the meeting, we'll have to evaluate the time that we have, and we may have to defer some of the images that came in late until next month. But we'll try to get them in, and all of you observers and imagers can help us by keeping your discussions short. And I'll close off the meeting at the end with announcements. Next one, please. Okay, we've had 95 new members in 2025. That is awesome, and I welcome each and every one of you. I hope you enjoy your stay with us, and I think you'll find the club very interesting and informative, and a lot of opportunities to do some cool stuff like our star parties and our facilities out at the FLO Observatory near Almont. Next one, please. We have members in the news. We have Jim Thompson, and the next one, please. Jim has authored an article in the 2026 Observer's Handbook on filters. As you know, for those members that have been with us for a while, Jim is our resident filters genius and has provided us with some wonderful insights into the use of filters and how they can aid both our visual observations and our imaging. So he's going to dive into that, he's diving into that on this very extensive and well-written article. Congratulations, Jim. Okay, and just a quick reminder, the 2026 calendars are, I believe we've received them, or if not, we'll shortly. And there are 4 pickup locations in Ottawa that you can let folks know that you're interested in one of those locations to pick it up, or you can pick it up at the dinner meeting if you're planning to attend our annual dinner next week. Alternatively, they'll also be available for pickup at the next meeting, which will be live in addition to Zoom, and will be at the Canadian Aviation and Space Museum. Just a reminder of the cost: $20 for one and $18 for multiple copies. Price is $25 for non-members. Next one, please.
Okay, I'll pitch in here,
and,
Paul.
Chris, I'm going to let
next few slides.
Yeah, I'll let you take that one.
So just a reminder that next month, December, as always, in addition to our monthly meeting, will be the annual general meeting of the Centre, where we summarize the year's business and give awards and elect members to council. So that will start at 7:30 next month at the usual time. It will be available only to members online, but in the theater there'll be both people, members and non-members. Here is a draft typical agenda. The actual notice of the AGM will go out by email to all members sometime between now and December 5th. And that notice, when it goes out, will also include the initial slate of nominees that are proposed by council for election to positions, though there's always the opportunity for additional nominations to be received by any member wishing to suggest someone or to offer to serve. The only condition being, if you want to be nominated, you have to inform the secretary, which is me, at least 5 days in advance so that you're in the slate. So that's next month. It'll be preceded then by the normal monthly meeting starting at 8:15. There will be separate Zoom links, one for AGM, one for the regular meeting. But come in person to the theater and you'll be there at the Aviation Museum for both.
All right, thank you, Chris. And just a reminder too that I'll be part of that meeting, obviously, and I'll be announcing the winners of the or sorry, I'm looking for I'm jumping my gun here. I am gathering my thoughts and my short list for the annual awards that we have, including the Planetary Observing Award and the Paul Commission Observer of the Year Award. So today is the deadline. If there is anything else you want to present to me, please send it to me by midnight this evening. I've already received a bunch of materials, and I thank the submitters for that. And I'm currently still reviewing our presentations and our images that were given to our members, given by our members over the course of the year there. So I will be making my decision on the awards by tomorrow, and that's why I say if you have anything last minute that you wanna send me, please do so before midnight. Thank you. Next one, Chris. Oh, there we go. So Dave Chisholm, you're up on deck for Ottawa Skies for November.
Okay, excuse me. Here we go. Chris, next slide, please. So here are the moon phases for the month. Obviously, we've already experienced the switch to standard time, which is great. We can get out observing an hour earlier. So the full moon was on the 5th and was one of the second of the super moons that we're going to have this year. And the new moon is going to be on November the 20th. Next slide, please. We have the northern towards meteor shower. Now, I know it's November 4th and 5th. That's when it peaks, but it actually runs until into December. So don't hesitate to go out and see if you can see them. But right now, it's a bit of a challenge because of the we're just coming out of the full moon. And this meteor shower is unique in that there's two different radiants. There's the northern and southern radiant. 5 to 10 meteors per hour. So I'd wait till we've got less moon up in the sky, and then you might be able to see them. If you miss these ones, well, next slide. We have the Leonids meteor shower, November 17th and 18th. This time we have just a small crescent moon, so it won't get in our way. 15 meteors per hour, and these were produced by dust grains left behind by Comet Tempel-Tuttle. And it peaks on November 17th. Sunrise and set, you can see there's a bit of a jump there because of the change to standard time, but obviously the days are getting shorter until December 21st. Next slide. There we go. Mercury is not visible. It's rising and setting with the sun. And Venus is also not visible. It's rising same with the sun. Mars is visible at dusk. Yeah, but it's just at the edge there. It's just after the sun sets. Jupiter is visible in the evening and through the night, all month, as is Saturn. Uranus is visible in the evening and through the night, and on November the 21st, it's at opposition. That means it's closest to Earth. And Neptune is visible in the evening. And here is our cartoon of the month. Star Party. There we go. Thank you, folks.
Great, thank you, Dave. All right, next up on deck is Jim Thompson telling us about telescope mounts. Take it away, Jim.
Yeah, I'm just going to switch over to my screen here. Oh, sharing is not turned on presently. Oh, he's got it. Great. Actually, it's just share screen too. Okay. All right, everybody should be able to see my cover slide.
Indeed.
Excellent. Well, good evening, everybody, and welcome to my talk titled How Mounts Work. Tonight, I will give you an overview of the types of mounts that are available, as well as some background regarding how these mounts work. I will finish by sharing some of my personal experiences with a few different mount models. Let's start with a quick run through of the list of basic mount types, starting with type 1, human-powered. This type consists of simply holding the scope up in your hands. The type is very popular amongst old sea captains and has the quickest setup time. This mount gives the worst pointing accuracy, however, and it is impractical for large aperture telescopes. This type is meant for visual use only, but at least it costs you nothing. The next mount type is the standard camera tripod. To aim, you manually push or pull the tripod up, down, and left, right. Using a tripod is much steadier than by hand and permits a heavier scope to be used. Tripods generally are lightweight, portable, and quick to set up. They are, however, slow and clumsy to find and center objects. Because a camera tripod is not motorized to follow the Earth's rotation, constant re-aiming is required. Kind of like in the animation there. That's a typical night using a tripod. A camera tripod is suitable only for visual observing and imaging at very short focal lengths and exposure times. Camera tripods typically cost under $100 or up into the low hundreds. The next type is an Alt-Az mount with manual slow motion controls, as shown here. They provide the ability to finely adjust your aim up, down, called altitude, or left, right, called azimuth. This gives one the ability to aim accurately while maintaining a quick setup. Being a manual mount means you still need to constantly re-aim the scope in both axes to keep the observing target centered. This mount type is good for visual observing and for imaging at very short focal lengths or exposure times. This mount type can typically be purchased from around $100 to the low hundreds, although pricier models are available. Next are manual equatorial mounts, similar to manual Alt-Az, except the rotational axes of the mount are aligned with the Earth's axes, east-west and north-south, instead of left-right and up-down. As with the manual Alt-Az mount, accurate aiming is possible with this type, but one needs to polar align the mount and balance it prior to use. Again, being a manual mount means you are constantly re-aiming, but at least the mount only needs to be moved in one axis, the east-west axis called right ascension. This mount type is also suitable for visual observing and imaging at very short focal lengths and exposure times. And they range in price similarly from under $100 up to a couple hundred. The next type involves adding motors and a computer brain to the Alt-Az mount. Using a hand controller like the one that I point to here, or a Wi-Fi connection to your phone, these mounts give you very fine control over up, down, left, right movement. As a result, very accurate aiming is possible. In fact, you can simply pick an object in the sky and tell the mount to go to it. These mounts are relatively quick to set up, some even coming with a GPS antenna so it can figure out where it is and the local time automatically by itself. Once you confirm for the mount where it is pointing, it is able to track objects in the sky, compensating for the Earth's rotation. These mounts are great for visual observing, but can also be used for electronically assisted astronomy. So imaging at long focal lengths, but using short exposure times only. They range in price from around $400 to just under $1,000. The final type of mount to consider uses the same idea of motorized computer control, but with an equatorial mount. As with the motorized Alt-Az, you get very fine control over mount movement and accurate aiming and go-tos. Polar alignment and balancing are required, so setup time is longer than with an Alt-Az. But in exchange, you get the best tracking of all the mount types. These mounts are good for all applications, whether you are a visual observer or a serious astrophotographer. They come in a broad range of prices, from around $400 up to over $10,000. An important reason for why there is such a large range of these mounts available has to do with the issue of load capacity. Here we have the range of motorized equatorial mounts sold under the brand name Skywatcher, a well-known and well-respected mount brand. These mounts all vary in physical size, but also vary in terms of how powerful their drive systems are, how robustly they are built, how much counterweight they have, and thus how much telescope equipment they can effectively carry. The value in kilograms shown here is the manufacturer recommended load capacity for each mount. Note how the price of the mount quickly ramps up with increased load capacity. Now let's switch gears and talk about mount drives. If you're at all serious about the astronomy hobby, it is likely that at some point you will own a motorized mount. For this reason, I thought it would be helpful to explain how mount drives actually work. Mount drives are required to deliver very large gear reduction ratios, meaning a large change in speed from the motor speed to the drive speed. Tracking mounts move very slowly to match the Earth's rotation, but they are also required to deliver high torque. This has an impact on what drive types are suitable to use. There is also a lot of pressure to keep mount manufacturing costs low, which also impacts what types of drives are used. There are several different kinds of drive in use today, all of which consist of some sort of DC motor combined with a mechanical gear reduction device. Let's first talk about motors. This is an animation illustrating how a basic DC motor works. The motionless stators on the outside are some sort of magnet. So here and here. Often a permanent magnet, but electromagnets are also possible. The spinny bit, called the rotor, has a series of electromagnet branches on it, also referred to as the armature. As the rotor spins, each branch gets energized in sequence, creating a like and dislike magnetic poles that cause a repulsive or attractive force, respectively, between the stator and rotor. Electrical current flows to each branch via a set of contacts called the commutator, which rotates with the rotor. The speed of this motor increases with increasing voltage applied across the commutator. and increased speed means increased torque. A weakness of this design is the fact that brushes are required to rub on the commutator to complete the electrical connection, and these brushes wear out over time. There is also no feedback with this design as to where the rotor is at any moment in time. The big advantage of a basic DC motor is that it is cheap to manufacture. Any small toys or appliances that you have at home probably use this type of motor. Next up is brushless DC motors. For these motors, the design has been flipped inside out, with the stators being the electromagnets and the rotor being a permanent magnet. Digital circuitry controls when and for how long each stator coil is energized. This design requires no brushes. Speed is controlled by the timing of the controller pulses, and more torque is achieved by increasing stator voltage. Since a digital controller is required to drive these motors, they are more expensive than basic DC motors. They are, however, more reliable and more efficient. Most new applications of DC motors, such as e-bikes and high-end cordless power tools, use brushless DC motors. The final type of DC motor relevant to mount drives is stepper motors. Stepper motors are a type of brushless DC motor. They have many stator coils and multiple poles on the rotor, allowing for the motor to be rotated precisely in discrete steps of a known angle. They require an advanced digital controller and are the most expensive of the motor types used for mount drives. They are, however, very reliable, giving repeatable, precise control over speed and position. Now that we have some motors to choose from, let's talk about reduction gears. Here is an animation of the simplest gear design, a spur gear. Torque is transferred from the drive gear, in red, to the driven gear, in green, via a single tooth, limiting how much torque can be transferred. The reduction ratio is calculated as the number of driven teeth divided by the number of drive teeth. One can stack multiple spur gears in a cascade in order to achieve a large overall reduction ratio, what would commonly be identified as a gearbox. Spur gears, because of the single tooth engagement, are prone to backlash, essentially slop in the gears noticeable when you change direction. Spur gears are also known for their periodic error, a result of manufacturing tolerances causing every tooth of the gear to not be exactly identical. These weaknesses aside, spur gear drives are the cheapest to make, so they are very popular. Another common reduction gear design is the planetary gear. In this gearing system, the sun gear, shown here in green, drives the planetary gears in blue, which also engage at the same time with the fixed outer ring gear in gray. As the planetary gears orbit around the ring gear, the carrier to which they are attached, shown in red, also spins around and forms the output from this gear design. The reduction ratio is calculated as the sum of the sun and ring gear teeth divided by the number of sun gear teeth. If you stack multiple planetary gears using the driven gear of one as the drive gear of the next, you can achieve very large reduction ratios. Planetary gears require ample lubrication to function normally, and they are prone to backlash and periodic error like spur gears. They are, however, capable of transferring large torques, which makes them popular for applications like automobile transmissions. The next gear to consider is the worm gear. The drive worm has a spiral groove cut into it that engages with the worm wheel. As the drive worm rotates, the worm wheel teeth are carried along by the grooves in the drive worm. The reduction ratio is calculated as the number of worm wheel teeth divided by the number of spiral groove starts on the drive worm. A worm gear drive gives a large reduction in a single step, but they need to be well lubricated to function properly. They are also prone to backlash and periodic error, but these are easier to manage than with other drive designs because there are fewer interacting parts. One advantage of worm gears is that they can't be back driven. The friction between the worm and the worm wheel is too great for the wheel to turn the worm. This makes the drive fail-safe, meaning when the power is off, the mount won't move under the weight of all the mounted equipment. The final gear-based drive to consider is the harmonic gear, also called a strain wave gear. This reduction gear design was originally invented by Walton Musser in 1957. One notable usage of this gear design was to drive the wheels of the Apollo mission lunar rovers. They have only started to become popular for telescope mounts in the past couple of years. In this design, an elliptical-shaped wave generator, shown in green, deforms a cup-shaped flex spline in red as it rotates around. The flex spline is deformed to the extent that it engages with a circular spline in blue on the outside of the assembly. For every rotation of the wave generator, the flex spline advances 2 spline teeth. The resulting reduction ratio is calculated as the number of flex spline teeth divided by the circular spline and flex spline tooth difference. The harmonic gear is able to deliver a very large reduction ratio in a single drive step. Harmonic drives are significantly more expensive than other drive types, and they can be back-driven, so they are not fail-safe. And their periodic error is not better than any of the other drive types. Their advantage is that they have no backlash and deliver high torque at a large reduction ratio in a small size. The final speed reduction method to discuss is the belt drive, whereby a flexible toothed belt transfers torque between the similarly toothed drive and driven pulleys. Reduction ratio is calculated as the number of driven pulley teeth divided by the number of drive pulley teeth. Because of the space required, belt drives are typically only used for small reduction ratios, or when it is desirable to have a large separation between the drive motor and the mechanism being driven. Belt drives are sensitive to cold temperatures, and the belts eventually wear out and break. They, however, have no backlash, can deliver high torque, and have low periodic error. So we now have a library of DC motors and reduction gears to choose from. Let's look at some example mounts to see what sort of drive solutions have been applied by their respective manufacturers. My first example is of the first fully motorized mount I ever owned, the Orion Atlas EQG, which is essentially a rebranded Skywatcher EQ6. I found this to be a very sturdy and reliable mount. I am intimately familiar with the drive system for this mount because I upgraded it myself to a belt drive. After many years of service, I sold this mount and replaced it with a larger one. This mount's drive consists of 2 DC stepper motors. You can see over here on the left, which turn 3 brass spur gears. You can see the 2 here on the end of one of the motors, and the third one is where this pulley would normally be. This upper picture is during the process of it being converted to a belt drive. By the way, this mount at the time sold for around $1,500 to $2,000. My next example is of the first Alt-Az grab-and-go mount I ever owned, the iOptron Cube Pro. It is quite small and lightweight, which makes it perfect for taking to outreach events or to my cottage in the summertime. It gave me acceptable tracking, and the go-tos were pretty good for doing visual and electronically assisted astronomy. I cracked the mount open to do some customization, swapping out for a better dovetail shoe, improving the friction on the declination clutch, and adjusting the backlash on both axes. Eventually, I sold this mount to get something with more load capacity. Its drive consists of 2 basic DC motors. You can't really see them. They're hidden inside of these plastic enclosures here. And they drive multiple plastic spur gears, which you can see here. Plastic being known for its durability and high accuracy. You only use plastic when you want it to be cheap. This is a cheap drive. The plastic gearbox drives a brass worm, which you can see here, and that engages with an aluminum worm wheel. The drive also has an optical encoder hidden down here in the white plastic enclosure as well, to keep track of where the drive is pointing at any one time, since there is no position feedback provided by the motors. At the time I bought this mount, it was around $400. The mount I replaced the Cube with is the Meade LX65, another motorized Alt-Az. Even though it has a significantly larger load capacity than the Cube, it is still relatively lightweight and portable, and is quick to set up. I found the tracking and go-tos with this mount to be good, and I used it regularly for EAA and solar imaging. I especially loved the dual saddle arrangement, allowing me to mount 2 telescopes at the same time. I did have to do some repair work on this mount, however, when the declination drive seized up. It turned out to be a lubrication issue. I presently have this mount listed for sale, as I have decided to replace it with an equatorial mount. This decision being driven primarily by the fact that Alt-Az mounts do not track well when looking directly overhead. You get something called field rotation. The drive for this mount uses 2 basic DC motors. You can see here, there's one there and the other one over here. They drive a 3-stage steel planetary gear, which is hidden inside of this gray metal enclosure. So there's one there. So there's 3 stages of planetary gear in there, tiny little gears. That drives 2 brass spur gears here on the end, which in turn drives a brass worm. You can see it kind of in there, which finally drives an aluminum worm wheel. You can see clearly in this image the adjustment screw right here, which is used for adjusting how hard the drive worm pushes on the worm wheel, which is how you adjust the gear backlash. The drive has an optical encoder right here on the end of the motor, so you can tell where it's positioned. I bought this drive for just under $600 at the time, but they now sell for more like $700. My next example, some of you might remember from a previous talk I gave. It is the iOptron Skyhunter. It is very small and lightweight. I have found it to have good tracking and accurate go-tos. It can be used in Alt-Az or EQ modes. And there are several options for user interface: a traditional hand controller, connection wirelessly to your phone or tablet, or simply by using the buttons on the side of the mount. My only beef with the mount is the right ascension clutch is a little wonky. It is possible to tighten the clutch easily, but then it requires an inordinate amount of force to loosen it again. I successfully transported this mount in my luggage to Mexico for the 2024 solar eclipse, and I have used it on multiple occasions for EAA. This mount's drive consists of two basic DC motors. There's one here, and the other one is over here. And they drive multiple metal spur gears. There's a zoom in there of the gearbox. And that's followed by a belt drive here on the end, which drives a brass worm. You can kind of see the brass worm right there, which in turn drives an aluminum worm wheel. The optical encoder in this case is clearly visible on the back of the motor. You can see the sundial there and the sensors right there. The basic mount costs just over $400, but I added the optional hand controller and adjustable base, bringing the total price closer to $700. The newest mount in my collection is the Juwei 17, my replacement for the LX65. It is a Chinese-made discount harmonic EQ mount. Brand-named harmonic mounts in this load capacity range, such as the ZWO AM5, tend to cost in the $2,500 to $3,000 range. I purchased this mount for $1,400 off of AliExpress. It is quite portable, being fairly small and lightweight, but it also delivers high torque, being able to carry up to 13 kilograms of equipment with no counterweight. The mount delivers good tracking and accurate go-tos and is super quiet. You pretty much can't hear it when it moves at all. The mount uses an open source control board and firmware called OnStep, some of you might be familiar with, and comes with a dinky little but functional hand controller. The mount also has built-in Wi-Fi and Bluetooth as alternative ways to connect to the mount, but I found these methods to be unreliable. Connecting to the mount using a USB cable was a much more reliable way to control it. I have had an opportunity to use the mount several times now for remotely located EAA, and it worked great. Out of curiosity, I cracked the case open to see what was inside. Typical engineer. This mount uses two stepper motors. They're stacked on top of each other, one on top of the other here. That's the close-up there. And they drive a belt drive, which is kind of hard to see, but you can kind of see the two pulleys there and the one over there, which connects to the final harmonic gear. There's a harmonic gear in this cylinder shape here, and the other one's in this cylinder shape here. So that's actually the gear in that volume. So pretty compact, pretty simple, and it seems to work. My last example is the Skywatcher EQ8R Pro. This is a beast of an EQ with miles of load capacity, 110 pounds worth. You could put a small child on it. It is absolutely not a portable mount, the head alone weighing more than 50 pounds. This mount gives excellent tracking and go-to accuracy. It has also performed very well for me down to minus 25 degrees Celsius. This mount is permanently installed presently on a pier in my backyard, and at any one time has an assortment of 2 or 3 telescopes mounted to it. I have not dared to open this mount up, but I did manage to find a YouTube video showing what it looks like on the inside. It uses two honkin' big stepper motors. There's one there and one there. They're about the size of my fist, so huge. And they are either directly driving the worm gear, such as in this case here. There's just a flexible coupling and it directs directly to the drive worm. That's the declination axis. Or it's connected via a belt drive, as you can see here, for the right ascension axis. Despite using stepper motors, which have their own built-in situational awareness, the mount has an additional set of optical and magnetic position encoders. You can see there's the sensor there, and this is a magnetic positional sensor here. It goes all the way around. It's for additional pointing accuracy and the ability to move the mount by hand and have it still know where it is pointing. I purchased this mount, just the head, for $4,500 in December of 2019. It now sells for $6,750. Thank you, tariffs. Adding the appropriately huge tripod brings the price tag up to $8,100 Canadian. So that is about it. You are now up to date on my experience with telescope mounts. Hopefully, you all now have a better understanding of how mounts work. In parting, I have a few last tidbits of wisdom to share with you. Your enjoyment and success as an amateur astronomer relies heavily on you having a good mount, one that is solid, performs well, and is appropriately sized for your application. It pays not to cheap out. Get as much mount as you can afford. You will thank yourself later. For visual observers, an Alt-Az mount with slow motion manual controls is probably good enough. However, if you can afford a decent tracking mount, that is even better. For EAA and solar system imaging, you are okay using a motorized Alt-Az mount, but you may meet with some limitations, such as your maximum sub-exposure time. It's going to be around 20 to 30 seconds, and field rotation. So a motorized EQ mount would be better. For long exposure imaging, so sub-exposure is longer than 30 seconds, you're going to want to have a solid motorized EQ mount. Remember to pick a mount with a load capacity greater than what you plan to mount on it. Well, that is it. Thanks for listening. If there are any questions, I am happy to answer them.
Chris, do we see any questions on the board?
Well, no, I'm not seeing any questions. There's been some chatter in the background, but no questions.
Excellent.
Awesome.
Moving on.
Well, thank you so much, Jim. That was awesome.
You're welcome.
All right. Next slide, please, Chris.
I'm trying to find it. And I'm struggling. Sorry, we have developed questions. From Doug Fleming, how important is balancing?
So for a traditional EQ mount, it is very important. When you have a mount with a large load capacity, it is going to be able to handle being unbalanced a little bit, but you're still going to want to have the balance close. If you're using a lighter weight mount with a lower load capacity and you're pushing the amount of stuff you're putting on it, you absolutely need to take the time to balance it correctly in both axes, both right ascension and declination. It's important. Otherwise, the mount is going to struggle under the unbalance, and it's not going to work correctly.
Another question from Peter Hutchison about, please comment on lubrication.
I'm sorry, can you repeat that?
Please comment on lubrication.
Lubrication. Yes. So a lot of that has to do with where you're using the mount. So the mounts all come with some default lubrication in them, assuming that we all live in a temperate climate where there's no humidity, you don't have temperature fluctuations, that sort of thing. So if that's the case, and you're an occasional user, you'll probably never have a problem with lubrication. But if you're using your mount in the wintertime, sometimes the lubrication is not good for cold conditions, and you need to change the lubrication, like the type of grease used. In other occasions, like on the LX65, the lubrication that they used did not like high temperatures. So I had the mount sitting down on the beach while I was on vacation. It was covered, but it was still exposed to ambient temperatures. And it evaporated all of the grease out of the planetary gearbox. So I had to disassemble it, clean it all up, and put an appropriate lubricant in there that was able to handle the higher temperatures. So these are the kind of things that can crop up depending on how you're using the mount.
Okay, from Carry Power, what's the best reason to use Alt-Az over EQ?
The best, the primary reason is the ease of setup. The newer Alt-Az mounts that have a built-in GPS antenna and all the brains, you basically set it down and you turn it on and it's good to go. There's no balancing, there's no polar aligning. So it saves a lot of time with setup. You just turn it on, you point to your first object and say, this is where you're looking, and you're off to the races. So that is the main reason to choose Alt-Az over Equatorial, is the ease of the setup time.
And then from Rick Wilson, how far are we from tolerable self-aligning polar?
I'm sorry, I didn't catch that.
How far are we from tolerable self-aligning polar? I think polar alignment.
Oh, self-aligning polar? Well, I've never used a mount that can align itself with polar alignment. I'm sure they exist, but it sounds expensive. It would mean motor, like the picture that's on the screen now. These are all equatorial mounts. And this mechanism down here at the bottom, I don't know if you can see my mouse going around, maybe not.
No, you're not using your screen.
So in the center image that's shared on the screen, you can see the red knob that's close to the wooden. Yeah. So all of that, there's two things to adjust there: your up, down, and your left, right. That would have to be motorized to make it automatic. So that's just adding more complexity. And there's a lot of weight. Like, look how much weight there is in this image, all hinging on that one point. So it would have to be a really strong, high torque motor to be able to move that, to be able to automate it. So at the moment, it's not out there for the consumer. It's all manual.
Okay, and the last one from Doug Fleming. How accurate is the polar alignment routine in the SynScan?
SynScan. I haven't used that Atlas mount now for about 10 years, so I can't remember how good it is. But there's now lots of technology solutions to to help you with the polar alignment problem. So for example, I use SharpCap, the software for doing my EAA. And one of the tools built in is polar align routine, where it'll take an image, you rotate the mount manually, you take another image, and it'll say, okay, you need to move your mount left this much and up that much to be polar aligned, and you're done. It's very easy to use. There's no getting down on your hands and knees looking through a polar finder scope to get your polar alignment.
Okay, and the last follow-up question from Carrie Power. Do motorized mounts need to be stored at a particular temperature or other conditions to prevent deterioration when not in use?
That's a good question. Typically, any electronic device, it's bad to bring it inside from being out in the cold for a long time. It's bad to bring it inside and turn it on. So if you're just bringing it inside and leaving it somewhere to slowly come up to room temperature, that's generally okay. So the two mounts pictured on the left, those are both portable type mounts. So at the end of the night, I might leave them out overnight, or I might bring them inside depending on where I'm located. The black mount on the right, that stays outside 365 days a year. And both of those use cases I have not had any trouble with. As long as you protect it, if you leave it outside, you need to protect it from the elements. Otherwise, you're okay.
Says a lot, Jim, that you had so many questions. Lots of interest level. So
Yeah, that's good.
thanks. We'll move it back to Paul.
Great, thanks a lot, Jim. That was super informative. I'm sure you've cleared up a lot of questions from a lot of people, including myself. So thanks again for spending the time and going into the exquisite explanations that you've given. All right, next slide, please. Chris, can we have the, oh, there we go. Okay, I'm going to roll through this quickly. We have many benefits for those of you who are visiting us tonight and considering the RASC as a club to join, or as the club to join. Next slide, please. First of all, certainly the membership. We have an extensive membership of very knowledgeable people that are all too willing to share their knowledge and expertise to help you out on your own astronomical journey. It's a huge benefit of our club. Next one. Also, we have a telescope loan library and a book library as well for use by members. We also have the wonderful Fred Lossing Observatory out near Almont, which offers us a reasonably dark sky, and we have 3 very functional telescopes in their own observatories there. So huge benefit for members. These are for use by the members only. And you can certainly, using these instruments, earn numerous of the RASC observing certificates that are available. Next one, please. Great. We also, as a member, you also get the yearly Observer's Handbook, a super definitive guide on many subjects related to astronomy, including Jim Thompson's article on filters, but also very detailed monthly details on what's in the sky and planetary information that'll assist you in your observing. You also have access to our monthly astronotes, and basically the journal, which is published by the RASC National Center, that is yours as well. Next one, please. Members also have access to the pro version of the Astrospheric application. This is a great perk for our club there, as it gives you access to a tool that offers a wealth of information to aid your observing and your imaging, specifically things like site conditions and predictions for observing different objects at different times and different locations at any time of the year, current time of the year. Also, you have access, as a member, you have access to the Discord server where you can share ideas and imagery with fellow members. And these are all wonderful benefits that will keep you busy when you're not attending our RASC meetings. Next one, please. Just a note, there has been a slight increase to the membership prices from the national RASC national. Regular membership is $118 per annum. Family membership is $112.50 plus $18 for an additional adult, and $10.50 for a youth member. And we also have a youth membership for those under 21 years old, and under 25 if you're a student. Then that comes in at $7.40. A bargain at twice the price for sure. Next one, please. Okay, you can ignore that side, that one obviously, since we're not at the museum this month. We are going to take a 5-minute break, and before I forget, I just wanted to make one clarification on the awards that I mentioned right at the beginning of the meeting. The Rolf Meyer Award on the slide was listed for planetary observing. Oh, thank you for getting that up, Chris. For planetary observing. It's not just planets, it's anything in our solar system. So we're talking, the moon, planets, obviously, comets, anything that enters our system or is part of our system, that is is available for observing and or imaging. Those are all applicable as well. So thanks for picking that up, Mick, and I'm glad I had a chance to make that correction.
Just Chris.
Okay, well, let's ignore me then. It's finally coming now. Now I see.
Alrighty, here we go. Since it's finally there. From grandparents to children, we all look up at the moon, and we always have, and some more intently than others. I think it's fair to say that the latter category includes many of us here at this meeting. Who has not looked at the moon through the binoculars or through the telescope? When we look at the moon, it raises all sorts of questions in our minds. Some of them, the questions, disarmingly simple. It's just, okay, what am I not doing right here, Jim, to advance?
Page downward.
There we go. Okay, page down. All righty. Now, one of those seemingly simple questions is, how high is the moon in the sky tonight? And why? This simple question was at the heart of the most difficult presentation I ever had to put together for a RASC Ottawa meeting back in 2012, I believe. Another seemingly simple question might be, how far away is the moon? And how did it get there? But that simple question raises a whole host of other potentially complex second-order questions as we seek to provide an answer to the initial simple question. One of those second-order questions is, how has the Earth-Moon distance evolved over time? Now, you probably know that the present orbit of the moon is elliptical, which means that the Earth-Moon distance varies at the scale of months to years, hence all the media hype about supermoons. Sorry, Dave. The usual average distance in the literature is about 385,000 kilometers, that you can round out at about 400,000 kilometers. It's easier to remember. But you're also aware that current thinking derives the moon by a collision between a very early Earth and a Mars-sized planet called Theia, which means that the moon must have started off very close to the Earth some 4.5 billion years ago. So what's it doing way out there at 400,000 kilometers distant now? Well, obviously the Earth-Moon distance has increased with time since 4.5 billion years ago, but how? And why? More supposedly simple questions. Now, a recent paper published in December 2024 set out to address these very questions. Notice the title. It doesn't even mention the Earth-Moon distance. Why? Because we have no way of directly measuring the history of the Earth-Moon distance in the past, but there are proxies. So what's a proxy? Well, a proxy is something you can observe and or measure that has a known or inferred relationship to something you cannot directly observe and or measure. Well, it turns out that the Earth-Moon distance and the length of the Earth's day and the rate of precession, or the wobble, of the Earth's spin axis are all related. Now, this is so important, I'm going to repeat this. I want you to just hang on to these three factors. The Earth-Moon distance, the length of the Earth's day, and the rate of the precession or wobble of the Earth's spin axis are all related. So if you can work out the rate of change through time of one of these phenomena, you can at least get an estimate of the rate of change of the other two. An estimate. Now, you might think that this is getting unnecessarily complicated. Most of you probably already know that the length of the Earth's day was shorter in the past. The Earth was spinning faster, and that it has slowed down to about 24 hours as the Moon has drifted further away from the Earth. Now, this is due to an exchange of angular momentum, also known as tidal drag. But what you may not know is that this evolution of the length of day and the Earth-Moon distance has not occurred at a constant rate. Look at the end of the title of the paper. Earth's precession, or wobble, the Earth's precession wobble rate changed rapidly towards the end of what's called the Proterozoic era. In other words, between about 1 billion years ago and 500 million years ago. And that's where the complications come in. In this figure from the paper, as you move right along the horizontal axis, you're getting closer to the present day, and the precession rate is getting slower as we move down along the vertical axis. Now, note that the modern rate of precession today is 50 arc seconds per year. Keep this number in mind, 50 arc seconds per year. Now, before we look at this slide, which we will do, what exactly do we mean by precession, or wobble, and the rate of precession, or the wobble rate? You're all familiar with the behavior of a spinning top, and many of you know what a gyroscope is. As a spinning top slows its spin, it begins to wobble. Technically, its spin axis begins to precess. So precession can be thought of as the wobble of the axis of spin of a rotating body, including that of a planet. And that goes for the Earth too. A full Earth wobble today takes about 26,000 years. So its current precession rate can be described as 360 degrees divided by 26,000 years, or a degree every 72 years, or 50 arc seconds a year. Remember that number? That's how it's derived. But this diagram from the paper shows us that Earth's precession rate was different in the past. You can't fit all the data points here on a single line. That line there does not link into that line there. And here are the data points. Something changed between about 1 billion years ago, which would be here, and 500 million years ago, either slowly or rapidly at about 600 million years ago. But what might have caused that change? And before we can answer that question, we need to know where the data points in this slide come from in the first place. And the key word here is cyclostratigraphy. Okay, what is cyclostratigraphy? These are images of layered sedimentary rocks deposited in water. Not just any old layers, but rhythmic layers reflecting the seasonal cycles in the way that the sediments were laid down through time. And time gets younger going up in any of these sequences because they're undisturbed. They've not been turned upside down or anything crazy like that. So keeping things admittedly overly simple, if the visible layers were to represent years, then the really thin layers which would occur within the visible layers could represent days. So these thick layers here, which are probably in the order of meters to tens of meters thick, would contain thinner layers. You can see thinner layers in here. There's a thick layer of purple stuff with thin layers in it. Now, if we can count the daily layers within annual layers, then, since the Earth's orbit has not changed significantly over time, it's still the same distance, a year is still a year. We can determine the number of days in the year, and hence the length of day at that time in the geological past. Now remember, the length of the day is linked to the rate of precession of the Earth's spin axis. So if we know the age of the sequence of sediments that yield data on the length of the day at that time, we can put a data point on the graph. So as an example, it turns out that about 1.4 billion years ago, the length of day was about 18.5 hours compared with 24 today. A precession cycle took about 14,000 years compared with 26,000 years. And the Earth-Moon distance was about 340,000 kilometers, as opposed to 400,000 today. You can also do the same thing using seasonal growth rings in fossils, such as corals and stromatolites. You all know what a coral is. So here's an example of stromatolites that can be found at the foot of the Confederation Bridge on the Quebec side of the Ottawa River, when the river levels are low. And what you're looking at is a 450 million year old reef of mounds or domes of bacterial mats which have been beveled by erosion. So you can see concentric growth rings, if I can get this. I don't think I can. Trying to get the mouse over, but maybe it's got, oh, there I go. I went the wrong way. See these concentric growth rings where it's the same kind of thing as the layers we saw in the rocks. And these growth rings inside the mounds, they can be used as well to determine how many days there were in a year and how long those days were at the time. So, okay, we now know how to tell the length of a day at some specific time in the geological past. How does that help us to determine the rate of precession at that time? Okay, I know, it's an equation, but once we stop panicking and look at it, it starts to make very simple sense. Here's the equal sign. So let's start on the left-hand side of the equal sign, and we've got a small k. And this is the rate of precession, the rate of the wobble of the Earth's axis of rotation. Now go to the right-hand side of the equal sign, and we find all the variables you would expect to influence the orbital mechanics of the Earth-Moon system. For example, x, I'm having trouble finding there we go, there's the x here. That's the length of the Earth day. A, you see A over here in several places. That's the length of the long axis of the Earth's elliptical orbit. E sub E and E sub M, that's these things here and this over here. Those are the ellipticities, either circular or elliptical, of the Earth's and Moon orbits, respectively. I, which is in here somewhere, I will find it. There it is, there's I. I is the inclination of the Moon's orbit with respect to the ecliptic, and capital M subscript M and capital M subscript S, they're over here. They're the masses of the Moon and the Sun, respectively. There are no surprises here. Then, with a few necessary assumptions, based on some rather clever statistical analysis, by the magic of mathematics, one can calculate the rate of precession for the geological time in question. Miracle. By doing this for a number of dated geological formations, we can then plot the evolution of the precession rate of the Earth through time. But what about those necessary assumptions? Well, we don't actually know the true values for a number of the variables in the equation, especially those relating to orbital eccentricities and inclinations. So many older studies simply assumed a circular orbit for the Moon in the same plane as the Earth's rotation, and modern-day values for pretty much the rest. One of the major contributions of the authors of the work I'm describing to you here is that they used a neat statistical analysis to go beyond these assumptions and put some realistic numbers on these variables, but we'll pass on the details here. The other assumption most workers make is that the only influence on the orbital mechanics of the Earth-Moon system is the famous tidal drag. And I'll bet dollars to donuts that this is what you were all taught in school too. Possibly even the oldest among us, since this all dates back from, I can't remember if it's the father or the brother of Charles Darwin. So here's a quick reminder of what we mean by tidal drag. Both the moon and the sun exert a gravitational influence or pull on the Earth, which is most readily seen by examining the ocean tides. But the moon is closer. So the gravitational influence of the moon is more important than that of the sun, from our point of view. The moon's gravity raises a tidal bulge. It's easier to conceive over here. A tidal bulge of water on the Earth that follows the Earth's rotation and gets ahead of the moon, which orbits more slowly than the Earth turns on its axis. So this leads to a tidal bulge offset. That's the offset between the axis of the tidal bulge here and where the moon is sitting with respect to that bulge. With the tidal bulge leading the moon and pulling it forward and speeding it up in its orbit, and the moon trailing the tidal bulge and trying to pull back on the Earth, and therefore slowing down its rate of spin. Now, the same tidal interaction occurs between the rocks of the Earth and those of the moon, but because rocks are stronger and stiffer than water, the effects are visually less spectacular, but of greater magnitude in terms of angular momentum. Now, remember your thermodynamics. For every action or interaction, work has to be done and energy exchanged. And in the case of the Earth-Moon system, this results in an exchange of angular momentum from the Earth to the Moon, whereby the rotation of the Earth gradually slows down, the precession and wobble rate of the Earth also slows down, and the Moon speeds up in its orbit and migrates away from the Earth. In a nutshell, this is a story of tidal drag that many of you will already be familiar with, except perhaps for the wobble part of the story. The problem with the assumption that all of this is due only to tidal drag is that in order to account for the change in precession rate of the Earth at 600 million years ago or thereabouts, the tidal drag effect has to take 40 times longer than it does today. But we don't have an explanation as to why. So this paper challenges the assumption that change in precession rate of the Earth at 600 million years is also explained simply by tidal drag. And the paper asks, what other factors could influence the precession rate? Earlier in this talk, I compared the precessing Earth to a wobbling top or gyroscope. But this is an oversimplification. In reality, the Earth's outer layers are not uniform, as you can see by looking at the distribution of less dense continental rocks versus denser ocean rocks, plus the distribution of the mass of ocean water. So if you like, you can think of the Earth as a weighted spinning top, weighted in the same sense that the cheating gambler's dice might be weighted to come up with sixes, as opposed to a random result. To add to this complication, continental drift, due to plate tectonics, means that this weighting effect has changed through time. Just compare the distribution of continents and ocean floor here today with what it looked like about 250 million years ago. However, there's also the possibility that the redistribution of surface mass due to the formation and melting of polar ice caps through geological time, or perhaps even a planet-wide ice sheet known as the snowball Earth, might have affected the precession rate. But, as the authors point out, once you remove the ice, the planet should return to its pre-perturbation precession rate, and the Earth did not do so. So then the paper looked at changes in the interior of the Earth at the scale of the planetary core and mantle. And as a reminder, Earth is a differentiated planet, differentiated into a thin outer crust, a thick rocky mantle, and a metallic core that is liquid on the outside and solid on the inside, as you can see here in this exploded diagram. So could the formation of a metallic core have affected the precession rate at about 600 million years ago? Well, no. There is firm evidence that the metallic core had already formed by 4 billion years ago. So what about the crystallization of the solid inner core from the liquid outer core? Remember that the solid inner core has crystallized from this liquid outer core. That doesn't work either because the transition from liquid to solid is a phase change. It's not a transfer of mass. So, almost in desperation here, what about a disturbance of the solar system itself? There's lots of stuff in there to disturb. This would lead to major changes in orbital eccentricity that would leave very obvious evidence of major change in the sedimentary record. Now, you might say, great, maybe that's what snowball Earth was all about at about 600 million years ago, except that we should see similar disturbances on the other planets at that time, and we don't. So finally, and this really is desperation, the paper even looked at how lunar-driven tides in the Earth's atmosphere might contribute to changing the Earth's precession rate, and unsurprisingly, they drew a blank. The atmosphere is simply not viscous enough to affect precession. So, what did the authors of this paper conclude? What was their take-home message? Well, having eliminated all the other potential influences on the Earth's precession, they are left with the very unpalatable conclusion that the change in the precession rate has essentially got to be due to tidal drag, even though they have no mechanism for explaining why the time required for the tidal drag to be effective at 600 million years ago has to be 40 times longer than under modern-day conditions. So what's my take-home message here? Well, to quote the old adage, all models are wrong, but some are more useful than others, and combine it with a direct quote from the authors regarding their own analysis, quote, "There are many uncertainties in the uncertainties." This paper well illustrates how much we still do not know about our nearest astronomical neighbor, even with respect to some of the simple questions we might ask of it. Clearly, there's still much to be learned about the Earth-Moon system. As always, thanks for listening.
Thank you very much, Simon. That was wonderful. Just wondering if we have any quick questions. If not, I have a very quick one myself, Simon. And how certain are we of that time frame of the 600 million years for the change in the precession rate? How accurate do you feel that is?
The authors, this is a wonderful paper because it's one of those papers where the authors are really upfront and transparent about everything. They don't know. They're quite clear. They say, look, there's a 400 million year time period here between 1 billion years ago and 600 million years ago. It could have been a progressive change, or it could have been abrupt, because if we just drop back a couple of slides, we should be able to get to the, let's see, but maybe, yeah, go.
I'm now displaying the slides, Simon.
Okay, Chris, don't worry, it's going to be further back than I thought. There are actually no data points in that 1 billion to 600 million year gap. We really need to find there we go. We really need to find a sedimentary sequence in here that will give us more than just this one data point that's sitting there, and it's on the end of this line. We need a data point in there, and in fact something up here too. We need to find some sedimentary sequences which we can date, and where we can perform this kind of calculation. So lots of room.
In the meantime, Simon, there's a question for you. Interesting one. If the moon were to fall out of orbit, how would that affect tidal cycles on Earth?
Oh, if the moon fell out of orbit, then our Earth would stop behaving like the well-behaved gyroscope that it is now, and it would just go nuts, just like your kid's spinning top, just before it's actually about to skid and crash into the wall. It would be absolutely catastrophic.
The title effects might be irrelevant to us.
Exactly. Well, I don't think you call it tide anymore.
Certainly a bad hair day.
Bad hair day, indeed. Indeed.
All right, I think we need to move on. Thank you again, Simon. That was lovely in its details and as usual in your excellent mode of presentation. All right, we're going to jump to our observation reports, of which we have, as you see from the list, many. In fact, I don't, in my many years with the Ottawa Centre, I don't seem to recall seeing a list of observers that long, even through special events like the eclipses and such. So obviously lots to share, and we'll jump right in. Our first contributor is Bob Olson.
Just before we jump in, Paul, can I just ask every presenter to remember where they are in the sequence and pay attention who they follow so they're ready to go?
Oh. Yes, that's a good reminder. And obviously, I'm just going to reiterate my point. Please keep your presentation crisp. Thank you. All yours, Bob.
Thank you. The Andromeda Galaxy, or M31, was very well situated in the sky for me to image this month. So that's what I decided to concentrate on. Next slide, please. This rectangle is my field of view with my telescope and camera. You can see that it is way too small for something as large as the Andromeda Galaxy. This meant that I was going to have to construct a mosaic. My first image is the one that I have outlined on this slide. As you can see, it is pretty small compared to the galaxy. If you're going to do a mosaic, the first rule is square up your field to the field of view so that it lines up with the subject. In my rush and complete disregard for common sense, I didn't do this. Next slide. This meant that the minimum number of panels that I would require would be 15 instead of 10. The double lines represent the needed overlap between images. Otherwise, you will never be able to align the panels. Next slide, please. The first problem that I had was that I do not own any software that will automatically place the individual panels on the image. This meant that I had to guess where to point my telescope next. I would check with which parts of the image that I was missing and attempt to find them in the sky. Instead of the minimum number of 15 panels, I ended up needing 26. After I had all my images, I then had to assemble them in a mosaic. Over the 9 nights, I acquired 332 individual images. This added up to 55 hours of exposure. These images were spread out over very different sky conditions, some more moonlight, sometimes more cloud, and different heights from the horizon. This meant that all the images varied slightly in color and intensity. This made processing them to be all the same, a nightmare. This processing adventure took 2 weeks. I did not use a logical labeling scheme, so I lost track of where some of the images were in the mosaic. This was a big problem in parts of open sky. Even though this was way too much work, both in acquisition and the data in processing the data, I am very pleased with the final result. It is without doubt the deepest image I have ever taken. To me, it is a very stormy and spooky looking place. Thank you.
Well, good evening, everybody. 3 weeks ago, off the north balcony here in the city, I imaged the Heart Nebula, and on the same night, about 2.5 degrees south of it, the Soul Nebula. The Heart Nebula is an emission nebula 7,500 light years away in the constellation Cassiopeia that displays glowing ionized hydrogen gas and darker dust lanes. The bright part at the bottom is the Fishhead Nebula, NGC 896, which is 6,000 light years away and is adjacent to the larger much larger Heart Nebula. These images represent 19 minutes of live stacking with the Mellencamp Skyraider camera using the William Optics 61 millimeter refractor at f4.7. I also used a new light pollution filter, the Antlia 3 nanometer dual narrowband that I discovered reading Jim Thompson's review of various filters and was impressed with its performance. I'm just getting my feet wet using such a filter, but already I've noticed the contrast and brightness of the H2 emissions in some of the images that I've taken. Next one, please. The Sol Nebula is also an emission nebula in Cassiopeia with several open star clusters embedded in it. Another common nickname is Baby Nebula, as it resembles the shape of a baby. The Heart and Sol nebulae complex spans an area of approximately 300 light years and are connected by a bridge of gas. I was surprised at the degree of internal brightness and structural contrast that I got with this particular image compared to previous images of the Sol that I took with the same gear, except the filter was different. Previous times, I used the Ideas MBX dual band nebula booster, which is quoted online as 10 nanometers, versus the Antlia filter at 3 nanometers, which reduces much more light pollution while capturing H-alpha and oxygen-3. The exposure time, however, was greater with this filter, but worth it in the end. Both images presented were post-processed with Topaz Studio 2 and Affinity Photo 2. Next one, please. And here is a solar animation that I took about a month ago with periodic brightness, unwanted periodic brightness occurring caused by passing clouds. The main prominence is quite interesting, as well as the action along the limb and the small prominence to the left, which is suspended above by the magnetic field. Thank you.
That's a joke. That's awesome. That's good. Look at this.
Thanks, Jim.
You're welcome.
Next up, Paul Osmond.
Yes, hello. Can you hear me?
Yeah, thanks.
Yes.
Right, thank you. Thank you. Hello, everybody. So this month, I did the October challenge that was presented by Richard last month. So basically, this is the region of the Milky Way near the constellation of Cepheus. So, and I must confess that I cheated here. I actually used one picture, and I kind of got all the targets in in one shot. So besides the challenge objects, there are some other targets in here as well. Upper right, you'll see that orange glow there. That's the Elephant Trunk Nebula, which is IC 1396. In the middle there's some other nebula, the Lobster Claw, which is Sharpless 157. And you'll see the Bubble Nebula, which is NGC 7635. Right at the lowest part of the frame there, it's kind of the bottom leftish part of the frame. That's the Pac-Man Nebula. And so to take this image, it was with my DSLR and a 35 millimeter lens stopped down to f4. And my DSLR is a full spectrum modified. And it also has a light pollution clip-in filter. Next slide, please. So I plate solved and I annotated the image. As you can see, Cepheus is on top there, or half of it. And you got Cassiopeia on the bottom, and Lacerta is just on the side there on to the right. So again, the Milky Way goes from kind of bottom left up to the top right there. And this whole field of view is about 38 degrees by 25 degrees. Now, next slide, please. So we'll take a closer look now at the challenge objects. So in the inset, you'll see two objects, which is Delta Cepheus, which is the that bright star there with the green circle around it. It's the famous Cepheid variable star used to calculate the distance to galaxies and other similar stars. Just below that, we have the open cluster NGC 7380, which is a new open cluster, and it's a part of the Wizard Nebula complex. And the Wizard Nebula is a big stellar nursery for those new stars. Next slide, please. So a little bit further down, you see the question mark nebular complex. So there's basically two objects in here. The big one is the open cluster NGC 7822, which is in kind of the lower part of the nebula. And the question mark itself, the whole complex, was also part of the challenge objects. Also slightly below is Sharpless 170, which is also considered part of the question mark. It's kind of the little point of the question mark. And you can see there's other little things in here as well. There's little clusters, that NGC 7762, and all throughout that Milky Way, you'll see a lot more of those. So at this point, I had two options. I could either collect a little bit of data on all the targets rather, or I could just pick one target and collect a lot of data. So I chose the latter, and I chose the Wizard Nebula. So next slide, please. So this is my shot of the Wizard Nebula. It's an it's a Hubble palette image, an SHO. So that's sulfur in the red channel and hydrogen in the green channel and oxygen 3 in the blue channel. So you're looking at about a little over 20 hours worth of integration time here. And this was taken using my RC6, which is a Ritchie-Chrétien, roughly 1370 millimeter scope. And I had an Astro camera with an IMX585 sensor in it. I kind of left the stars in because really the pardon the pun, the star of the show is the open cluster, which is 7380, and which is a big part of this nebula system and where the nebula gets its energy to kind of glow like that. So yeah, so in this image, you'll see lots of different things. You'll see lots of dark dust lanes, little glowing nebulous parts. You'll see like cosmic cliffs, Bach globules, and lots of different things like that. It's kind of interesting to me because I think this nebula is kind of on its side. I sort of get the feeling that the nebula is kind of hollowing out that chasm or valley kind of in between the two walls that you see there. And I sort of think that, like I said, the nebula is tipped on its side. And I think if you were on top of that nebula looking down on it, it would look a lot like the Lagoon Nebula, with a kind of big, bright glowing center. But you can't see the center because, again, those dust walls are kind of blocking things. Next slide, please. So we'll take a little closer look. So here you see, again, we have examples of pillars of creation. You can see in the kind of the lower right part of the inset, you can see that glowing red part there, and the pillars kind of being backlit by hot young stars on the inside and probably just on the outside of it. In fact, I fully expect that if you look just outside the inset, it's kind of facing that other glowing bubble of gas there, that kind of pinkish red glow there. I fully expect if you're able to see that that pillar from the other side, it would look similar to that brighter red one there. So in the middle here, you have like the cosmic cliffs, right? So you have that U shape being sculpted out by the intense stellar winds and radiation of the cluster. And just up towards the top left there, you'll see that little clump of gas that's kind of calved off from the main gas cloud. And you can see that little red dot kind of on top of it. So Bach globules are known to be big star forming regions. And so I fully expect that is a kind of a proto-solar system being formed in there. Sadly, I don't have the resolution to bring that in closer, right? Because I suspect you could probably see a little more out of that. Next slide, please. And just more of the same, some more pillars of creation and some cosmic cliffs. Same story here. Obviously the pillars are being lit up and by stars on the inside and the outside. Very common, that U-shaped kind of cliff, right? That's also being sculpted out. And you can see just down below, it looks like there's some, what could be in the future, after you add another few million years perhaps, some Bach globules being formed there, but I don't see really any stars forming in those right at the moment. And that's it. So thank you.
Okay, thank you, Paul. In the meantime, the other Paul, Klauninger, has developed some internet issues and has been coming and going from the meeting, so we'll push on and hope that he can come back to join us. In the meantime, we'll move on.
I'm good right now, Chris.
Okay, great. He's back.
No worries. Thank you. Okay, Jim, long time no hear.
Or you caught me in the chat. All right. This was from the 14th of September. I believe last month we had an image from Andrea showing the same storm. I was on my way back from the cottage, having done some work to get it closed for the winter. And I knew something was going on before I left. I thought, oh, it's not a very big storm. It's kind of nice, but whatever. And then as I was driving through Cobden, I turned my head and it's like, what the heck is going on over there? So I pulled to the side of 17 highway, transports flying by me, and I took this picture. And it was quite an amazing display. Very bright, very, very active, very fast moving. So yeah, that was quite a treat on my drive home from the cottage. Next image, please. So observing challenge for this month, we just saw Paul's awesome image there of the Wizard Nebula. This is taken on two very different dates. The one on the left was a recent EAA session I had the end of September. This was from a cottage in the Calabogie area, visiting my buddy Waldo. We had a great night, beautiful clear skies. This is about 20 minutes total of 30-second sub-exposures, I believe it was. 3 nanometer dual band filter and I think that was the 80 millimeter refractor. So yeah, lovely night. Great to see even the extended nebulosity out in the perimeter here. And then the image on the right is a close-in looking only in H alpha from 2019. This would have been from my backyard in Ottawa from the 10-inch RC scope. And you can see some of the detail that we saw a moment ago, but not nearly the detail pulled out. But still from my backyard where it's borderline skies, not too shabby. Next image, please. This is another of the observing challenges for this month. LBN 581. The close-up shot on the left was taken with a 10-inch Ritchie Chrétien in my backyard with a 3 nanometer, actually it could have been 2.5 nanometer H alpha filter. That would be 30-second frames stacked for about 15 minutes or so. Actually, sorry, I'm looking at the focal lengths here. I've got the scope wrong. Yeah, 348 millimeters. That's not. Oh no, sorry. What F was that? No, that's from a 60 millimeter refractor with a reducer on it. So you can see some of the nice detail in the center of this object. There's some similar pillars in here. Very, very cool. You can see kind of mid-lower portion of the image on the left. Cluster in the foreground and lots of interesting detail in the dust, the dark dusty nebulas. So that's pretty cool. And then if you back way out using an 85 millimeter camera lens on a just a regular monochrome astro camera, you can see sort of the whole picture of what's going on. And this is called the cosmic question mark. It's actually it's identified as two different objects. It's got a Sharpless name on the lower, smaller object. These were both captured that same weekend at Calabogie Lake. Nice dark skies. Both, like I said, 30-second sub-exposures for about 15 minutes or so in an EAA session there. So fun night and some cool results. Next image, please. While I was there, I couldn't help but have a final look at the summer constellation of Cygnus. So that's why I've titled this Goodbye Cygnus. It's heading into the west now as the snow approaches. These are both shot with the 85 millimeter camera lens. If you talk nice, I will prepare a talk about using camera lenses to collect astrophotos. We'll see about that in the future. But yeah, lovely wide field of view. Lots of the emission nebulae in this area of Cygnus. Very interesting area to explore. Next image, please. Oh yes, there's a inset showing the setup that I was using. So that's the 85. It's a classic Pentax lens on the end. I had it set to f2.8, I believe. I put the filter on the end with an adapter on the front of the lens. And then that is a SV Boni SV605 monochrome camera. So yeah, that turned out to be a pretty good setup for that night. Yeah, the lens is f1.9, but I had it set to 2.8. Next image, please. And so this was my most recent observing session from my backyard. This was with the 10-inch RC scope, an IR pass filter to block as much light pollution as possible. On the column of objects on the left side of the frame were the observing challenges from last month. M15, the Superman galaxy, and then another NGC galaxy that was buried in some nebulosity. I'm sorry, Richard. I tried to catch the nebulosity, but it's from in the city. It was next to impossible to see. Maybe from a darker site. But in Pegasus and the area of Cetus, which are prominently overhead this time of year, lots of interesting galaxies to explore. This is just a sampling of the 16 galaxies I explored that night. My favorite being the Sculptor Galaxy, NGC 253. Lots of fascinating detail to see there. And I think, is that it for me? I think so. Yep. All right. Thank you.
Yes.
Thanks a lot, Tim.
Hello. Of course, Comet Lemon was all over the news and all over Facebook and all over social media for the past several weeks. I was struck by how much the ion tail changed that some people had managed to capture, and was able to do an acceptable job myself on 3 non-consecutive nights. Basically, I couldn't do it from the backyard because I couldn't see that part of the sky. It was far too low in the north, or in the northwest, sorry. From left to right, 23 October, that was about 5. These are all 30-second exposures. On the left, that was about 5 minutes. The middle is 11 minutes, and the one on the right was 30 minutes. Needless to say, I was struggling with the moon, which was starting to show itself. I was struggling with car headlights, and because the thing was so low in the sky, I started struggling with tall grass and tree limbs. However, that's you can see how much that the dust tail, of course, remains relatively constant, but it's that ion tail that is being swept away by solar wind, I believe. And if you go to the next slide, that's simply the center one in its full size. And that's what I would like to share this month.
Thank you, Mark.
There. Good.
You're muted, John.
There. Okay, this was taken October 26th, I believe. It was a long string of cloudy nights, and it was the first opportunity I had to take a picture using my C-STAR telescope. And I regret I should have rotated it. That's one of the drawbacks of the C-STAR. It uses portrait mode, so I should have rotated that before submitting it. But anyways, you can see several features. You can see the yellowish dust tail, which is reflected sunlight. You can see the bluish ion tail. It has a little bend in it due to fluctuations in the solar wind. The ion tail from its spectrum is made of singly ionized carbon monoxide. And then you can see a sort of, on the coma just ahead of it, a blue-green color, which is cyanogen, which is carbon-nitrogen compound. And that was a 5-minute exposure. And even in 5 minutes, there was a little bit of trailing. So I'm surprised how Mark was able to get these multiple exposures without having either the comet or the stars trailed, because I did take one 15-minute exposure and it was badly trailed. But anyways, I did get one satisfactory one. It was about 18 degrees above the horizon at the time. Okay, next picture. This is a duplicate of an image that I took last winter, again with the C-STAR. This is 40 Eridani, or also known as Omicron 2 Eridani, or KIDE. And one thing unique about it, it's if you're familiar with the original Star Trek universe, the planet Vulcan supposedly rotates around that star. It's the entire system is 16.2 light years away. And what makes it really unique is that the companions are really the only practical dwarf stars that can be seen with amateur telescopes. These stars are so low luminosity that they really can't be seen much beyond about 25 light years, which is right in our backyard. But the bright star is 4.5, the white dwarf is 9.7, and the red dwarf is 11.5. And the way I got a better image this time was what they used to call a hat trick. I used my hand basically to limit the exposure to 3 seconds, because otherwise the minimum is 10 and the companions got blown out and overexposed. And that red dwarf is one of the lowest mass stars known. It's only 0.2 solar masses. And the white dwarf is about half a solar mass, even though I believe it's about the size of the Earth, and yet it's half the mass of the sun. Okay, next image. And this was my latest attempt at M42, except I used the mosaic mode this time, which gives it something like a 2 by 3 degree field of view, which is twice what you normally get with it. One interesting thing, though, is that just above it, there's like 2 stars, and in there is what's called the Running Man Nebula, which is a blue reflection nebula, but it's almost completely wiped out simply because the C-STAR put in the nebular filter, which isolates only the oxygen and hydrogen wavelengths. And if you look closely, you may be able to see a little bit of red in there. So despite it being mainly a reflection nebula, there is a little bit of hydrogen emission nebula in there as well, which I wasn't aware of. But okay, that's it for me.
Okay. Good evening, everyone. Oh,
Go for it, Tony.
okay. Good evening. So I've got a couple of images from the Observing Challenge as well. This first one is the Wizard Nebula in a more of a wide field and in SHO narrowband. So this is my field of view. So I thought I would try and pick out a few extra objects nearby. The Wizard Nebula itself is sharpless 142, and all around the nebula here there are another, I think, 8 sharpless emission nebulas. If you sort of go up to the top middle, you can see, I think, 5 little emission nebula up in the center of the image. And over on the right-hand side, there's another couple of little emission nebulae, all in the sharpless catalog. So if you go to the next slide, then I've cropped it down to just the Wizard Nebula. And yeah, the SHO narrowband, you can really sort of pick out the blue oxygen and the sort of orange-red sulfur and hydrogen. I think I've got, I should have quite a lot of data here, so I'd like to go back and process this to really bring out some of the contrast in the dust regions that some of the other images have highlighted. These images were actually collected just a little bit before Richard told us what the challenge objects would be. So then that motivated me to get on and do a quick process this month. So in the next image, there's the other of the challenge objects, which is the top of the question mark nebula. This I actually took about a year ago and hadn't really got around to processing. So again, this is quite a large nebula. This is the same field of view as the wide field a couple of images ago. So you can really tell the scale difference. And you've got some nice hot young stars in the center that really make this emission nebula shine. In fact, I think I read that one of the hottest stars identified in our galactic neighborhood is located in the center of this emission nebula, and that's creating some of the structure that we can see in there. So again, I've got quite a lot of data from here. This was taken last year and processed just last week. So that's it. Thank you.
Good evening, all. So late October, I had what I think is the first ever night for me of 3 binocular comets. So I was able to image some of them, and another one besides. So going in reverse order, starting in the morning sky, comet 2025 K1 Atlas is it was lowish in the morning sky, going into twilight. So this is 10-inch f4 Schmidt-Newtonian with an ASI 294 mm camera, just a luminance filter, 28 times 2 minutes exposures. The comet was quite bright in the binoculars, 8x42 binoculars, but really hard to tell it was a comet because the nucleus is so bright. The coma is quite faint and small, and the tail was almost invisible. So it was it mostly just looked like a star. Next, please. So this is the one I didn't catch in the telescope. You can see right in the center of the field, there's some stars and then a little faint fuzzy blob. This is comet P29 Schwassmann-Wachmann, which is a periodic comet that I've imaged on a number of other occasions. So while I was sort of pointed in that direction, I picked that off as well. And this is just 8 2-minute exposures. Next, please. So also in the evening sky is Comet 2025 R2 Swan, which is fairly high. It's transiting, I think now about sort of 8 or 9 o'clock and up like 45 degrees high. It's in binoculars, it was just a big amorphous blob, no noticeable nucleus at all, no tail. And this is a collection of 19 2-minute exposures, and you can see it does show some concentration and hints of a tail off to the right. It was very easy in binoculars, but very diffuse, just a big amorphous blob. So now that the moon is disappearing, this is another good one to look for. Next, please. So one of the problems with Comet Lemon, first I observed it in early October. I can't see it from my house, so I have to walk down the road about a half a kilometer carrying my camera and tripod and barn door tracker and everything and binoculars, and found a place where I could see it through the trees, and looked at it and decided, nah, I'm not getting up at 5 o'clock in the morning to see this stupid thing. I mean, I've seen it once, that's all I need. So I waited until it started coming up in the evening sky, and then of course forgot that it was coming up in the evening sky for several days. So finally, I think it was about the 26th, it's still not visible from my place. So now I walk 3/4 of a kilometer down the road to the public boat launch where I can see it. And I rapidly learned to start driving down because I'm taking the camera, the tripod, barn door tracker, 2 pair of binoculars, and my 8-inch Dob. So this is with a Canon 30D, 100 millimeter f2.8 macro lens on a barn door tracker. This is 15-second exposures at f4. And 37 of them. It took rather more of them than I planned because while the camera was shooting, I was looking at the comet through the telescope and also doing an estimate of T-core bore. So then next image, the twilight was getting a little darker, so I went to 30-second exposures and f2.8, and you can see it's picked up a lot more detail in the ion tail, and of course the dust tail curving off to the right. It was quite easy naked eye, possibly hints of greenish coloring to it, about a half a degree tail, naked eye. Binoculars and telescope and stuff, it was huge. It was really tough. I mean, as well as the ion tail shows up in the pictures, it was really difficult to try and pick it out of the glow of the dust tail. And one of the things I noticed while I was looking at it and while I was processing the individual frames from the camera is the ridiculous number of satellites that are going through the field. I mean, the telescope with 1.5 degrees field of view, I was sometimes having 4 satellites moving through the field at the same time. So normally when we stack images, we do what's called a sigma stack. And so anything that's extraneous to one image and not general to the series effectively gets statistically sampled out. But if you do a maximum stack, in other words, just take the brightest pixel from all the images, you get the next image, which is a picture of all the satellite trails. So next image, please. Is it coming? There we go. So that's sort of just the brighter satellite trails that went through during a period of maybe 10 minutes, 10, 12 minutes. And you can see also my old camera, there's a whole lot of hot pixels drifting from lower left to upper right. I need a new camera. So that's all I've got. Thanks.
Thanks, Rick. I'm still waiting. I may have a bit of lag here because of where internet. Oh, there we go. Okay.
Clearly a lag, but it's someone called Paul's doing this next one.
Yeah, it's come up on my screen now. Sorry for the lag. So this is an image from my travels earlier this summer. It's a shot of sunset on planet Earth, taken on the north shore of Lake Superior. As I've mentioned in the past with previous views from this site, it's one of my favorite places for wide field astroimaging, given its very dark skies and broad open vistas. Next one, please. Maybe you can let me. Oh, there we go. It came up. And last month I was up camping on Cedar Lake near the Brent Meteor Crater, and lucked out with some wonderful skies. Like the North Shore of Lake Superior, this is an area that offers very dark and clear vistas since it's located in northern Algonquin Park, which is certainly a very sparsely populated area. This was a lovely moonset over the very still lake that night. And in the dark skies that followed that night, you can see my next image. Thank you. So I was treated to an amazing show of not only the northern lights that night, but also a rare and visible, actually visible to the naked eye, red star arc crossing the Milky Way at the upper right. A red diffuse aurora is seen at the left side, and I showed a few wider field views of this last month of this evening, taken with a 16mm lens. This image was taken with my second camera that I had running at the time, and it was with a 24mm lens. So you can see some very nice detail both on the Milky Way and on the aurora and the star arc phenomenon. I love the way they crossed over the Milky Way. It certainly was an unusual opportunity for me. All right, next one, please, Chris. All right, and so October, certainly, as you can see from the numerous and many images that were submitted, October was certainly offering us some clear and very pleasant evenings. While the moon was up on some of those nights and put a bit of damper on deep sky observing and imaging, certainly the moon's high elevation and the closer proximity this month and the favorable librations did make for some great high resolution views of our nearest neighbor, such as this image of the South Polar region. This was taken with my 11-inch Edge HD and an ASI 294 MC imager, and it's an infrared view with a 742 nanometer bandpass filter. Next one, please. So this is Comet Swan. October gave us some wonderful clear nights for fleeting visitors, as you've already seen with some of the wonderful shots that were submitted. Comet Swan, C2025 R2, no exception here. This view was captured with the same configuration as the lunar image that I just showed, so it gives you an idea of the actual size of this object as seen from Earth in our sky. So as you saw from the lunar view, that didn't cover much of the moon. Likewise, Comet Swan isn't a big comet, and as Rick noted, it's a bit unusual there. It has a very extended gas halo, but only a barely noticeable tail extending from the center and in my image down towards the bottom. It is a binocular object. I had no problem finding it with binoculars, and on the night that I photographed this, which was the 25th, certainly the skies were at their best, and it is questionable whether I could make this out visually. I think I was hallucinating, but certainly in binoculars, it was a treat. It was very easily visible. The next shot, if you would, Chris. This is the next shot is a time-lapse sequence of this comet, comprising 20 shots that I took over over a 15-minute period, 45-second exposures with the same configuration. You can see its movement there. So you can make out the dust, the halo, the gas halo surrounding it. Depending on your monitor and your brightness settings and stuff, you may just be able to make out even an extended version of that halo beyond the green that is fairly easily visible. So a nice comet, certainly not very big, but photographically and through binoculars, certainly worth a view. And my last image, if you would, Chris. Undoubtedly, the showpiece of our October skies was Comet Lemon, as you've seen in the numerous wonderful images taken by our members. October the 25th was certainly the finest night for this object from my location. And unlike Comet Swan, this object was easily visible under dark sky to the unaided eye. It was a real treat through binoculars as well. This particular image was taken with my Canon 70D and a 180 millimeter lens, and it's a stack of 13 30-second exposures taken over an 18-minute interval. Diagonally across this image, the field of view spans 6 degrees, or about 12 times the diameter of the full moon. So you can see it's substantially larger than Comet Swan was, and it was a beautiful object. The challenge was the moon at times over during that period of time in late October, and the fact that the comet was quite low to the horizon when dark skies finally set in. These shots were taken at an elevation of just around 15 degrees above the horizon. And as you can see, there's just some lovely structural detail in the tail here. That you can some wiggles and some curves. And if you look at the bright part of that tail along it, you can see that there are actually variations, noticeable variations in the brightness of the material being ejected from that comet. So almost like there were pulses of bursts of material being released, and they just scale back along that trail. So fascinating object, certainly the best comet of the year in my estimation. And that's it for me. Thank you.
I will continue the comet observations pictures that I took on 25th, the same time as Paul did, and Rick, I believe, as well. And it's again the same R2 Swan comet, probably around the same time of evening. I got similar results with a bright core and slightly visible tail, which extends to, in a direction that stars were moving, or actually in the same line as the stars were moving. I used 135 millimeter lens, so the field of view was quite large, and it explains the rather blob of light with not much details visible in a tail, because, as Paul mentioned, it really produced brighter greenish glow, while the details in tails were practically unnoticeable. Let's go to the next one. Same night, we were there with Konstantin Popov shooting the Lemon Comet, or I think it's called 2025 A6 Lemon Comet. So it's now probably the most observed object as for October, the one which was the most fascinating, was really easily observed from FLO with naked eye. We were able to spot it easily. Look in the binoculars, was magnificent view. And I took this picture with the same, actually this was with kit lens on the star tracker, where the image was stacked separately for the comet and separately for the foreground. The comet was peaking a few days later. Let's go to the next slide. Yeah, so this is stacked image of the same comet from the same FLO location, but it didn't show up, unfortunately, much of details for me. It was, as Paul mentioned, quite a struggle to get better contrast in the sky towards, in that case, towards Almont, no, Arnprior rather. The light dome which we have to the west at FLO is a bit noticeable, and it was difficult to separate the darker sky from the details. They were kind of consumed by the light dome from that in that direction. Let's go to the next one. I had a bit better luck a few days later on October 29th when I went to Westmeath, and I used my star tracker again with 135mm lens. However, this was also 50mm kit lens, and the view is towards Pembroke and Cobden. So the comet was southwest in that direction, quite visible, or barely visible rather by naked eye, but very nicely visible through binoculars. Let's go next slide. And this is from the other location, or rather from Westmeath Lookout as well, with a couple of images stacked with quite bright moonlight in the sky, plus some, you can see the traces of stars moving, sorry, of the clouds moving. So it was not the perfect observation night, but more details showed up because of the darker place. Let's go to the next slide. And my equipment, which I used. So this picture, I'm showing it only because it was taken with the cell phone, and it's only 8-second exposure. It's equivalent of 3200 ISO. You can spot the comet to the left of that bright streak, which is a trace of the airplane, but to the left of it, above, just below the cloud, there is a faint star with the tail, which is the comet itself. And again, this location is the same, Westmeath, near the gazebo at the top of the hill. Thank you.
Hi. This is a video of Sentinel-1D rocket booster, which was taken on November the 4th around 6 p.m. And if you include the wispy parts of this, it's pretty much as big as the moon. It was very bright. You pretty much had to know when to look for it because it only lasted about 5 minutes, traversing the western sky from south to north. It was launched on an Ariane 6 booster with the 2 solid rocket boosters strapped onto it. Typically, you would think of Ariane 6 launching satellites into GSO orbit, with the Ariane launch facility being in French Guiana, but it does do some of the heavier payloads like this one, which is a Sentinel-1D, which is very much like Canada's RadarSat. It does Earth imaging just as RadarSat does. So this was actually tumbling a little bit. I'm not sure if we have the video, Chris, or is this just the snapshot that I sent you?
There's the video.
Oh, okay. Yeah. And one of the reasons why it was so bright, it was dumping fuel, because when it went around the other side of the Earth, it was it had to fire some retros and dump fuel before it dumped the booster into the Indian Ocean just to the west of Australia. So one of the reasons why it was moving so fast, it wasn't even in orbit. Of course, you don't want rocket boosters to be in orbit. You want to get them out of there as quickly as possible. So this was a rather unique object, unlike anything I've ever seen. Thank you.
And the video's still going. There.
Hello. Can you hear me?
Yes.
Excellent. So I thought it would be fun to take you on a quick tour of the star-forming region of Sharpless 171 and NGC 7822, which hosted this month's challenge object LBN 581 in Cepheus. So given the limitations of displaying all the details in 1080p format, I want to begin with a quick Starship fly-through. So Chris, if you please engage the video. I don't know if it's just me, but the frame rate is not coming through too well. This was also put to music, but we'll just let it play through. I think I'll upload this video to the Discord so other people can experience what I intended to show tonight. Okay, thank you. Next slide, please.
Oh,
all right.
There.
So this nebula, which filled my field of view, is 5 by 3.5 degrees. I shot it over 5 nights, beginning late September and early October. I used my Red Cat 51 at 250 millimeters, a ZWO 2600 color camera, and a broadband Antlia quad light pollution suppression filter. The total exposure time is 31 hours, nearly 400 subframes of 5 minutes each. This was captured from my urban backyard, and I can highly recommend this filter, as I was very impressed by the faint background nebulosity, despite the city and the moonlit nights. Next frame, please. Here is a close-up of the dark nebula LBN 581. If you look carefully, it is possible to pick out at least one Bok globule towards the right upper corner, and other stellar nurseries. Bringing out the detail in the bright region and fine structures made this a very worthwhile monthly challenge object for me. Next, please. Next, I have a pair of star clusters. The larger one near the center, NGC 7762, and to the left, an obscure catalog, King 11. It has a population of around 50 stars, the brightest being only magnitude 11. Next slide, please. Finally, I found a delicate detail in a pair of reflection nebulae, LBN 585 on the left and LBN 590 on the right. That is all. Thank you very much.
Thank you, Andrew. Wonderful work.
Okay, so as we've seen from many others, the challenge objects were all in the constellation of Cepheus this month. I didn't get a very good picture of the constellation. I was trying out a new camera with a new zoom lens and didn't get it framed very well, but that was my best attempt. I did find that this camera has very, very fine resolution, so I had to intentionally blur this picture to make it show up on the screen at all. It's very nice when you zoom in on it, but the stars are such tiny pinpoints that they don't show up well for display purposes. Next one, please. Now, the other challenge object was Delta Cepheid, which is a classic Cepheid variable. And I took myself the challenge of learning how to use a new piece of software that goes into PixInsight and actually measures the magnitudes of stars. It's in coordination with the American Association of Variable Star Observers, so it makes use of their data on comparison stars. But I found fairly soon that I had to take extremely short exposures of this star because it is quite bright, magnitude 3.5 to magnitude 4.2. And that was too bright to measure unless you use an extremely short exposure. So I ended up using 1/10 of a second. So I would take a sequence of 10 or 15 0.1 second exposures and then run them through this software to find their magnitude and average it out. And with that, I did manage to get quite a lot of observations this last month. Actually, this is from September 28th all the way through October. And it was not a great deal of work to get the raw data because it would only take me a few minutes to set up, take the exposures, and I'm done. So I got 1, 2, 3 cycles of the star. Its period, as you see on the next image, please. The period is about 5 1/3 days. And what I've done here is taken all of my observations and then kind of normalized it relative to the period. So I've just shown the shape of a period, assuming that it's always the same, and it more or less does follow the same pattern every time. And this is what they call a shark fin pattern. Normally it would be the other way up because, of course, lower numbers of magnitude is brighter. So you get a fairly rapid rise to the peak in brightness and then a slow trailing off back into faintness again before it comes back and repeats the whole cycle. So I was kind of pleased with this package. It's got a bit of a learning curve, but not too bad. And it does seem to produce very nice results. So if anybody wants more detail about how I did that, just contact me. Next, please. And we've seen many versions of this. Thank you, everybody, for participating so much with these monthly challenges. So here's my version of the Wizard Nebula. I actually took this back at the end of August from the North Frontenac cottage that I rented. So nice dark skies, and it showed up very well. Next, please. And this is my version of LBM 581. Again, we've seen many versions of this tonight. Lovely area of the sky, full of both dark and bright nebulas and star clusters all over the place. Next, please. And then Comet Lemon. And I didn't get a picture of the challenge, the solar system challenge for this month, Jupiter's double shadows, moon shadows on, but with a lot of distractions, a lot of other things to observe. So this actually turned out to be a very difficult challenge for me because it's not visible from my backyard. I did go out to FLO a couple of times and it disappeared into the trees very quickly after sunset. So this is actually taken from Britannia Park on October 28th. And that evening I managed to get about 15 minutes of exposures, a combination of both 30-second and 60-second exposures with my ASI 2600 MC on the William Optics 73mm refractor. And like other people have pointed out, there's some lovely kinks and wiggles in the ion trail there. Came out very, very nicely. Now, if you look closely at this picture, you'll also see some artifacts. When I did the separation of the stars and the comet, there was a little bit of residual star trails in the comet images. Okay, so those are my observations for the month. And then moving on to the observing challenges. These were the ones for last month, and thank you very much for everybody who participated. Next, please. On the Discord server, there were a lot of pictures of the Wizard Nebula. We've seen some of them tonight as well, but we had other people like Bernie and Xavier and Andrea, always good participants on the Discord server. So if you're on that, go looking. I always post a separate thread for the monthly challenges. Next, please. So for this coming month, November, I hope we'll get some clear skies. It doesn't look so great right now, but I thought it would be good to have this, the challenge object. The very bright star that's rising in the east after sunset right now is Capella in the constellation of Auriga, the charioteer. It's also a kind of pentagonal shape, similar to last month's challenge, Sisyphus, but it's a bigger constellation, and as I say, it has this extremely bright star, Capella. You really can't miss it. And it's also connected on the southeastern edge with the constellation of Taurus. There's one star in the corner that's kind of shared between the two constellations. Now, across and inside Auriga are a lot of really, really interesting objects. So you'll see on this map here, I've marked 3 Messier objects, open clusters that go right across from the middle out the eastern edge of the constellation. M38, M36, and M37. So you should easily be able to see those in binoculars. I'm interested to see if somebody can catch a nice wide field view, a picture of all 3 clusters at once. But then going a little deeper, there's some very interesting nebulas inside Auriga. The Flaming Star Nebula, it's also known as Caldwell 31 or IC 405. It's not going to be visible to the naked eye, but or even the telescope eye probably, but it is quite good in the camera views. But the really interesting thing is that there's a star in this nebula, AE Auriga, and this is actually a star that started out in Orion's trapezium cluster and has been shooting away across the sky ever since, for about the last 2.5 million years. So it's a kind of interesting thing to take a look at anyway. And then fainter still is another pair of nebulas called the Spider and the Fly. This is IC 417 and NGC 1931. So if you go to the next slide, please. So those are the challenge objects in Auriga. And then for the solar system challenge, Saturn is really nicely placed for observing right now. And we're just going through another transition where the rings are almost exactly edge on. So I thought it'd be an interesting thing to start a long-term challenge, take some pictures of Saturn right now with the rings edge on, and then keep taking pictures of Saturn with the similar kind of equipment ever since for the next 10 years, and see if you can show the whole sequence of the rings expanding out to their open settings. Now, there's also an extra challenge that I haven't put on this slide here, but I saw a picture from someone else on, it was one of the astronomy image sites, but there's another thing inside Auriga at around 5 hours, 42 minutes right ascension, 36 degrees, 15 minutes declination. And it's really faint, but really big. So there's your mystery challenge for this month. Again, it's on the Discord server already. So if you want the details, go looking there. So good luck. Let's hope we get lots more pictures next month. Thank you.
Thank you, Richard. All right, that pretty much brings us to the end of our meeting. My connection has become rather unstable, so you may lose me here in the next minute or so, but the Fred Lossing Observatory is still available. We haven't had any snow flying yet there, so hopefully we can use that for a while. Next slide, Chris. And for the next Star Party, it is on November the 22nd, and it is at FLO. This is for members only, so you are more than welcome, and we'll cross our fingers and hopefully we'll get some clear sky. Next one, please. Club information. This information concerning the FLO and our loan library, etc. It is available on our astronauts, and those are the folks that are in charge of those particular areas. Next one, please. And thank you, everybody, for attending, and a special thanks to all the contributors, all the wonderful images that we saw. We did have 75 folks online tonight, so that's pretty good gathering for a Zoom. And we hope to have some clear skies and some great images for next month's meeting as well. Next slide, please. And the next meeting is Friday, December the 5th at 7:30 p.m. As Chris mentioned earlier in the program at the beginning, the first half of the meeting will be the annual general meeting. This is for members only. And other people that attend live at CASM, we will be back at the museum. And if you're tuning in remotely and on Zoom and you're not a member, then you can tune in at 8:15 when we will resume broadcast, and this will be the regular monthly meeting. So have a good month, everybody. Clear skies to all, and be safe and be happy. Thank you.